As an introduction to the use of the symbolic method to describe combinatorial classes while at the same time generating function equations for the generating functions of those classes. We'll look at trees and strings, which provide a rich set of examples all the way from the elementary to some of the most challenging combinatorial problems that have been studied. So the classic example of the symbolic method is trees. So how many trees are there with n nodes? Where a tree is described recursively as a tree. These are ordered rooted trees, so it's a node connected to a sequence of trees. And so these are the small values. There's 5 different trees of 5 nodes, and these 2 trees are different because the order is significant, and so forth. So these are the familiar Catalan numbers. And with the symbolic method, we can immediately derive the generating function for the Catalan numbers. So here's how it goes. So we define the class of all trees to be G. And then the construction, using the basic operations, we say a tree is a node and a sequence of trees. It's as simple as that. And just using the transfer theorem from the construction to the generating function that we just described, that immediately says that the generating function has to satisfy the equation z for the node over 1 minus g of z for the sequence of trees. G of z equals z times z over 1 minus g of z. In solving that, g of z minus g of z squared equals z. So that's an equation that the generating function must satisfy that we get immediately from the combinatorial construction, direct transfer. Now we can solve this one in particular using the quadratic equation. In classic analysis, the next steps are to use the binomial theorem to expand that, which is extracting the coefficients, and then with a little bit of algebra, we can get down to the result that g of n equals 1 over 4 minus 2 to n choose n. And then we can use classic analysis Stirling's approximation with, again, quite a few calculations to finally get down to the result that the number of trees is asymptotic to 4 to the n minus 1 over square root of pi n. And again, these types of calculations are what we covered in Analytic Combinatorics Part 1, if you're not familiar with them. If you are familiar with them, you know that there's a fair amount of calculation involved here. And again, what we're going to learn to do in the second part of this course is to use complex analysis, in this case singularity analysis, to immediately extract the asymptotic result. So that's what we're going to talk about later. For this lecture, we're going to look at lots of examples where we just stop at the generating function equation. So that's our goal, is use the symbolic method to derive generating function equations. That's what we're going to be talking about for the next couple of lectures. And then we'll go into how do we get the asymptotic results out. Now, a very standard paradigm for the symbolic method, and that really helps to explain or helps you to understand its power, is this idea of we use fundamental constructs to define things that are quite simple and intuitive. It almost seems too simple. Even trees, it's an extremely simple construction that gets us down to the result that we want. And sometimes they're very trivial or elementary, but at least we can check that they confirm our intuition and they indeed work. And we'll see plenty of examples of that. But then we can compound the constructs and immediately build up more complicated kinds of structures. There's lots of possibilities. The set of combinatorial constructions really is a language that has unlimited possibilities. And it turns out that even with the simple ones we've described, we can get lots of classic combinatorial objects that have been described, that have been studied in great detail. We can easily describe them with the symbolic method and get equations that the generating function satisfies. And what these constructs do is kind of expose the underlying structure in some way and then reflect that information in the generating function equation. But a lot of times we're just exploring one path to a known result for, again, the natural combinatorial objects, a lot of them that we're going to look at today. But the main point is that we can study variations where we try other possibilities. We have restrictions on things and so forth. And this is what comes up in practical applications, and there's an unlimited number of possibilities. But the structure that we learn from the fundamental and compound constructs just follows right through, and we get results that really we couldn't even consider approaching otherwise. And that's a very standard paradigm that we'll see in application after application for the symbolic method and for analytic combinatorics. It's a calculus for the study of quantitative properties of large combinatorial structures. And calculus means that really we have unlimited possibilities once we understand the basic operations. So just in the context of trees, let's look at a few very